Hey everyone, and welcome! Today we're going to peel back a layer of reality to look at something that's been hiding in plain sight, inside pretty much every material around us. It's a hidden set of rules called quantum geometry, and believe me, it's completely rewriting our understanding of matter itself.
So, let's just jump right in with a huge question. What if I told you that a material's most amazing properties, the things that make it special, were actually hidden? Not in a way we could see or touch, but in a kind of invisible geometry at the quantum level. That's the wild idea we're diving into today.
All right, to get why this is such a revolution, we first have to understand the map that physicists have been using for decades. A map that was incredibly useful, but, as it turns out, was missing a huge critical piece of the puzzle.
For the longest time, the main tool in the toolbox was something called band theory. Now, the best way to think about it is like a topographical map, for a mountain range. Except this map only showed you one thing: altitude. It told you the energy of every single electron. And look, it was fantastically successful. It's how we built our entire world of semiconductors and modern electronics.
And this quote just says it all, doesn't it? The old way of thinking was so focused on the big picture, on that altitude, that it basically decided to ignore the tiny atomic scale details. The thinking was, that's just noise. It probably doesn't matter for how all the electrons behave together.
Well, it turns out those details are everything. Our map was flat. It told us how high the mountains were, but it said nothing about their actual shape, how steep they were, or if there were any hidden twists and turns in the terrain. And it was in that missing geometry that a whole bunch of bizarre, unexplained new material properties were hiding.
So to complete the map, physicists had to look closer. A lot closer. Not at the energy of the electron, but at the shape of the electron itself. And what they found was this hidden structure.
Okay, let's start with a really simple case. If you take a single, lonely atom, like hydrogen, its electron just exists as this simple, fuzzy cloud of probability. It's predictable, it's a nice, perfect sphere. Super easy, right?
But of course, that's not how the real world works. Materials aren't single atoms floating in space. They're made of trillions upon trillions of atoms, all packed together in a tight, repeating grid. And that is where things get really, really interesting.
You see, when you bring those atoms close together, their simple little electron clouds start to overlap. They tug on each other, they interfere with each other, and they merge into this brand new, incredibly complex shape. This shared, tangled-up cloud is the quantum geometry. It's a whole new landscape that dictates the rules for how every electron in that material can move and behave.
So that brings us to the big question. What is quantum geometry really? What are scientists actually trying to measure when they talk about this?
At its heart, it's the language we use to describe this hidden texture. It's not about finding an electron's exact location. It's about understanding how its fundamental quantum nature, its wave function, stretches and twists as it tries to move from one atom to the next. And this geometry has two key ingredients. First, you have the quantum metric. You can think of this like a ruler. It measures the distance or the spread between quantum states, basically how much that electron cloud has to change its shape to get from point A to point B. But then there's the Berry curvature, and this is the really wild part. It measures a hidden twist in the landscape, a sort of invisible whirlpool that the electron feels as it moves around. Okay, so we've got this invisible landscape with its own sense of distance and these weird twists. So what? Why does any of this matter in the real world? Well, it turns out these abstract ideas have very real, very measurable effects.
And this is where the rubber meets the road. That twist we were just talking about, the Berry curvature, that is the direct cause of something called the anomalous Hall effect, where you can make an electric current bend sideways with absolutely no magnet. That's a huge deal for electronics. And that spread, the quantum metric, that controls something as basic as how well a material absorbs light. This isn't just theory anymore. These are things scientists are seeing in labs right now.
And the impact here is massive. This new way of thinking finally explains some of the weird behaviors we see in wonder materials like graphene. It's solving mysteries the old energy-only map couldn't even begin to touch. But maybe the most important thing is realizing this isn't some exotic, rare phenomenon. Quantum geometry is a fundamental property of all materials. It's been there the whole time, right under our noses.
So, if this hidden geometry is everywhere, what does that mean for the future? Well, it means we are right on the edge of a whole new revolution in how we design and engineer the world around us.
Think about it. For the first time, we're not just stumbling upon new materials by accident and then trying to figure out why they're useful. Having the tools of quantum geometry is like someone handed us the real, high-definition blueprint for reality. We can start to design materials from the ground up, engineering these invisible landscapes to get exactly the properties we want.
And the possibilities are just mind-boggling. This could be the key to unlocking stable quantum computers, new types of superconductors that work at much higher temperatures, ridiculously efficient electronics that waste almost zero energy, and even discovering entirely new phases of matter that we can't even imagine yet.
So we've just discovered this fundamental set of rules that has been secretly shaping our world all along. It really makes you wonder, doesn't it? What else is hiding down there at the quantum level? What other invisible geometries are just waiting for us to find the right way to look?